Imagine a spaceship daring to approach the edge of a black hole. At a certain point, known as the event horizon, something strange happens. The spaceship feels an incredible pull. It's as if an invisible force is dragging it towards the black hole. The spaceship tries to escape, but it's too late. It crosses the event horizon and vanishes from sight, trapped forever. But what exactly is a black hole? Imagine a massive star collapsing under its own gravity. As the star shrinks, its gravity becomes stronger and stronger. Eventually, the gravity is so intense that nothing, not even light, can escape. This is what makes them black and invisible to our telescopes. Black holes are not empty voids. They possess a real physical presence in the universe. The mass of a black hole determines its size and the strength of its gravitational pull. Some black holes are just a few times more massive than our sun, while others are billions of times heavier. As a star collapses into a black hole, it retains its angular momentum. This means that the black hole spins on its axis, just like our Earth. The event horizon is not a physical boundary, but rather a point of no return. Once something crosses the event horizon, it can never escape the black hole's gravitational pull. But how do we detect these invisible objects if they emit no light? The answer lies in their interactions with the surrounding matter and energy. Despite their invisible nature, black holes leave telltale signs of their presence. Astronomers have developed ingenious methods to detect these cosmic behemoths by observing their interactions with their surroundings. One way is by observing the motion of stars. Stars orbiting close to a black hole experience a gravitational tug that causes them to move in unusual ways. Another method is by observing the radiation emitted by matter falling into a black hole. These emissions act as beacons, signaling the presence of a black hole. Section 4. Einstein's legacy, predicting the cosmic abyss. In 1915, Albert Einstein presented his groundbreaking theory of general relativity, revolutionizing our understanding of gravity. Unlike Newton's law of universal gravitation, which described gravity as a force acting between objects, Einstein proposed a radical new concept. According to general relativity, gravity is not a force but rather a curvature in the fabric of space-time. Massive objects like stars and planets warp the space-time around them, just like a bowling ball placed on a trampoline curves the fabric. Einstein's equations predicted the existence of objects so massive and dense that they would create an infinitely deep curvature in space-time, trapping even light within their grasp. These objects, initially met with skepticism, are what we now know as black holes. General relativity not only predicted the existence of black holes, but also provided a framework for understanding their properties and behavior. Section 5. The quantum conundrum. When gravity meets the very small, general relativity reigns supreme in describing the universe on a grand scale, explaining the motion of planets, stars, and galaxies. On the other hand, quantum mechanics governs the microscopic world, dictating the behavior of atoms, electrons, and other subatomic particles. However, when applied to extreme environments like black holes, where gravity is incredibly strong and quantum effects become significant, a profound conflict arises. General relativity predicts that the center of a black hole, where gravity becomes infinite, is a point of singularity. Quantum mechanics, however, suggests that the concept of a singularity might be flawed. According to quantum mechanics, it is impossible to confine matter to an infinitely small point. The conflict between general relativity and quantum mechanics at the singularity of a black hole highlights a fundamental gap in our understanding of the universe. Section 6. Singularities and the unknown, peering into the abyss. At the heart of every black hole lies a singularity, a point of infinite density and zero volume, where the known laws of physics cease to hold. The singularity represents the ultimate unknown, a point where space and time as we know them come to an end. The concept of a singularity arises from general relativity, which predicts that the gravitational collapse of a massive star will inevitably lead to a point of infinite density. At this point, The curvature of space-time becomes infinite, and gravity becomes infinitely strong. One of the most pressing questions is what happens to the information that falls into a black hole. According to classical physics, information is never lost, but the singularity seems to violate this principle. Another challenge is the nature of time near a singularity. According to general relativity, time slows down as gravity increases. At the singularity, where gravity is infinite, time would come to a standstill. Section 7. Black holes. Gateways to the unknown. Black holes, with their immense gravity and enigmatic singularities, have long been a source of fascination and speculation. Some theories suggest that these cosmic behemoths may hold the key to unlocking some of the universe's most profound mysteries. One of the most intriguing ideas is that black holes could be gateways to other universes. This concept stems from the idea that the singularity at the heart of a black hole could represent a breakdown in the fabric of space-time itself. If this is true, it is possible that the singularity could connect to other regions of space-time, perhaps even other universes. Another intriguing possibility is that black holes could be the source of the mysterious dark energy that is accelerating the expansion of the universe. Some theories suggest that the immense gravitational energy of black holes could be contributing to this acceleration. As we continue to explore the cosmos, black holes will undoubtedly remain at the forefront of scientific inquiry.